Right. Thank you very much for inviting me and giving me an opportunity to talk about my work like this. So, my work is associated with SARS-CoV-2 virus. So, I suppose I don't have to tell what it is, but perhaps not everyone knows that SARS-CoV-2 virus has this capping machinery that ensures proper mRNS formation, and it involves four different enzymes. But we ourselves were more interested with NSP14 and NSP16, which are S-adenosyl-methionine dependent and perform methylation of guanosine cap in the position 7 and methylation of the next two nucleotides at the ribose sugar. This is how NSP10, NSP16 heterodimer looks like. There's always necessary this NSP10 partner for NSP16 to be actually active, so it's always a heterodimer. This here is its active site. This here is where the S-adenosyl-methionine is binded, and this here is where the RNA substrate is binded. So you can take a closer look here how it looks actually in a model. So this here is the methyl group that is further donated here to this sugar part. Our idea was then, and yes, you can see here that this cleft for this adenosine part is quite narrow, and there isn't much place to add anything, any large substitute molecules. However, around here with this RNA site and within this cysteine part as well, there is quite a lot of space where we can start to modify things, hoping to get some good inhibitors here. So this is why we call it dual site, that is occupying both SAM and RNA sites. So our design was then to leave this adenosine part as it is, and instead focus on this methionine part, so to add some larger groups, hopefully that would occupy the RNA site as well. And what we hoped most for here was that they would make some specific interactions with RNA binding pocket. So what we tried first was soaking approach, so we could get crystals with S-adenosyl-methionine in the active site quite easily. However, we could it was very hard to get upper form of these crystals because these crystals were growing very unwillingly, and also this active site pocket kind of changes conformation if there's nothing bounded there. So we then later switched to co-crystallization approach, which was very productive, with some inspiration from other colleagues in this field. So we so far had tested 31 inhibitors, and we obtained 13 different crystal structures with ligand in the active site. So, and what we concluded was that these ligands position themselves in three different conformations. One that is directed towards RNA away from S-adenosyl-methionine pocket. The second one, which is directed in alternative conformation, both towards RNA pocket and following this original S-adenosyl-methionine pocket. Or the third way, that it's located just in the S-adenosyl-methionine pocket and does not clash with RNA. So the largest group were the ones who matched this first mode, that is methionine substitute part, which was here directed towards RNA site away from S-adenosyl-methionine pocket. So here you can see our compounds, and in black are superimposed S-adenosyl-methionine here and RNA backbone. As you can see, what's common for all these compounds from this mode? So the electron density is quite good for this adenosine part everywhere. However, for this substitute part, this electron density is much more poorer. But it was still reasonable enough for us to conclude that it definitely clashes with the RNA substrate in all of these cases. However, there might not be some very specific interactions, or at least not a predominant mode of interactions with this RNA substrate site. And as you can see from the IC50 values here, all of these compounds are very, very potent. I mean, there's some who even have sub-nanomolar IC50 values. So these are very high efficiency inhibitors. Kind of interesting case was this compound for whom this IC50 value was a bit higher. So we're thinking perhaps because it's a bit smaller and doesn't clash so efficiently with RNA substrate, on account of that, its activity could have been a bit worse. So the second mode was that methionine substitute is in alternative conformation. So one conformation again clashes with RNA substrate here, and also the electron density is quite poor for it, while the other conformation that goes as the original S-methyl methionine positions themselves is much more. It has a much more better electron density, and it in one case actually copies the same interactions what S-methyl methionine forms in this active site. So as you can see here, these compounds are also very good inhibitors. However, the third group that followed precisely this adenyl methionine, you can see first thing here that the IC50 values are much higher, so these are not so potent inhibitors, and although the electron density is much more better for these side chains, you can have alternative conformations even here, but they still don't clash much with the RNA substrate. And even aromatic compounds as well are able to position themselves away from this RNA substrate. So, but the thing is, so what we could conclude from all of this that you need to occupy at least partially the RNA binding pocket for a very powerful, very efficient inhibition of this methyltransferase activity. However, there was one kind of a drawback, you might say, to this, because these compounds are not terribly specific. You know, they work, they're like a kind of like a sledgehammer. You know, it hits hard and hits everything equally. So it works quite well on human methyltransferases as well. So there's still work to be done if we want to make it more specific towards this methyltransferase or maybe other methyltransferases of other viruses. So that would be all for me. Thank you for attention.